Hi, my name is Will Franklin. I'm a mechanical engineer major from Leavenworth, Kansas.
Hi, my name is Tyler Golbus, and I'm a biology major from Columbia, South Carolina.
My name is Matt Monahan, and I'm a biochemistry major from Clemson, South Carolina.
My name is Jason Sade, and I'm a mechanical engineering major from Greenville, South Carolina.
And my name is Shreya Thamana. I'm a bioengineering major from Greenville, South Carolina. And this summer, my group and I worked on the computational cardiovascular research project with Dr. Ethan Kung.
In this project, we focused on modeling stenosis in the carotid artery. Carotid stenosis is a fatal disease caused by the buildup of plaque in the arteries that deliver blood to the brain. Here are some images of carotid stenosis. As you can see in the picture, there is plaque building up on the sides of the carotid dissection, resulting in decreased blood flow.
Using some vascular software, my team and I looked at CT scans of a patient and modeled the carotid bifurcation at the stenosis, stimulated the patient's blood flow, and analyzed the results to determine whether the patient's condition was severe enough to cause a stroke.
Here is an image showing the completed model of the carotid artery bifurcation in SimVascular. So here it shows the common carotid artery coming up from the heart. And then the bifurcation is where it splits into two different arteries, the internal carotid artery and the external carotid artery. The stenosis occurs on the bifurcation on the external carotid artery side, as shown in the image.
Here are some pictures showing how we created a model for the carotid artery bifurcation. We started by creating a path through the center of the carotid artery bifurcation section. Then we created segmentations by tracing the anatomy of the arterial wall throughout our section, around the path we had previously formed. Finally, we created our model, created the mesh, set parameters for the simulation, and then ran the simulation.
The ultrasound data we were given was also important to us. We took this data and used it to extract the velocity of the blood flow through the carotid arteries. We then took this velocity and multiplied it by the cross-sectional area to acquire the flow rate of the inflow and outflow. Lastly, we used Excel to calculate values using these formulas. To the right, you can see one of our input files for the simulation, which we had to create.
We were able to successfully create 5 separate models from 5 different patients. We then ran multiple small-scale simulations to test our models for any imperfections in the mesh. When we were sure the simulations worked, we ran vascular simulations over the SimVascular supercomputer to test our models. The simulations on this computer could take up to a few hours because of the accuracy of the computer. For these simulations, our mesh size was very small.
Here are the results from one of these simulations, which shows the pressure along the carotid bifurcation. We each ran our separate simulations and obtained results. In our research, we investigated carotid blood flow. Our simulations demonstrated the effect that carotid stenosis has on the biomechanics of the artery.
With our results, it can be easily seen that the computational cardiovascular research project shows lots of promise in its ability to accurately demonstrate physiological deficiencies.
In the future, we plan to run multiple simulations that will lead to reliable results. These simulations can be applied to biomechanical engineering research that is aimed at better understanding symptomatic and non-symptomatic carotid stenosis cases.
Thanks for watching. We hope to see you at the annual Eureka Poster Forum, which is Friday, October 23rd from 3 to 5 p.m.